Okay, you knew this was coming. All right. We have seen frequently when we get a function that looks like this plus 2x prime plus 10x or something. You're like, oh, okay, I got this, Jay. I believe you do got it. 4 minus 40 over 1, 2. So negative 2 plus or minus it's 36. So 6i over 2. So negative 1 plus or minus 3i. And you're like, oh no, that's weird. It is weird. It's a little weird. So what happens in this case? Well, you know you're going to have e to the negative t times some a sine of 3t plus b cosine. Oh, did it backwards. Well, it doesn't matter. You get the point. Same thing, right? Addition's communicable. Commutative. Yes. So there it is. So then the question then becomes, well, say that's weird. What happens in that case? Glad you asked, friend. Glad you asked. So what would the Laplace transform of that be? Ooh, interesting. So let's go ahead and do one of these guys. Okay, let's do this one here. Let's do e to the negative at cosine of kt. We'll go ahead and do that. Okay, that's all right with you. So we'll take the Laplace transform of that, and that'll be the integral from 0 to infinity of e to the negative at cosine of kt e to the minus st dt. There we go. So I'll combine some like terms here before we get going. So e to the negative t, and then it's going to be s plus a, I guess, yes? And then it's going to be cosine of kt dt. Oh, back in my day, which was not the good old days, I don't think. We had to do it all by hand. Now we have these weird people in math and college level now that think they're so woke or wonderful or something that we're going to defend math. We're going to make you all do it the hard way like we did. No, Jay is not doing that. Not going to happen, friend. Z plus, I'm just going to use X for A. And the reason why is I've not cleared my A for a while, so I don't know what's hiding in A. And so I could very well, on accident, like put a matrix in there or some ridiculous thing, and that just would not make me happy. I'd be very angry if I did that. Now, I'm just going to go 0t. You with me? Boom. Or just, oh, dang it. All right, so what did I get here? I missed off. I forgot to close the E. There we go. Cool. Done. Okay, so here it is. Oh, good Lord. We're in degrees. That's a problem. You need to be in radians. That's more better. Whew! So it's k sine kt. I'm going to write that down. K sine kt over. Now, this mess on the bottom, you're like, what is that crap? Just bear with me. You'll see. So it's going to be x squared plus 2x. So that's going to be actually a squared plus 2az plus z squared plus k squared. That's hot. And then you're going to get minus cosine of kt. Cosine of kt. Bottom is the same. Times z plus a. And then what else do we got? And then the whole, the whole shebang, e to the whatever, okay? So then e to the negative t, s plus a. Okay? Now we need to evaluate this at 0 and infinity. Okay, now, cool. If you plug infinity in for t here, these guys, they just bounce back and forth between 0 and 1. So it's nothing divided by infinity, so 0 on the top end. On the bottom end, if you plug 0 near, the sine of 0 is 0. So you're going to get 0. The cosine of 0 is 1. Then you're going to be left with, check this out now, this is important. It's going to be z plus a over, Now bear with me here. This bottom right here is going to be, now check it out, wait for it. This part right here factors z plus a squared. So z plus a squared plus k squared. Oh, that's hot. And then, again, at 0, this goes away. And so you're left with this. So s plus a over s plus a squared plus k squared. Now note the difference. This is the Laplace transform of e to the at cosine kt. This is the Laplace transform of cosine of kt. And what you'll notice is the only difference is wherever, when there's e's here, instead of putting in s, you're going to put s plus a. That's the only difference. Wait, are you saying then that the Laplace transform of the sine of, of e to the at sine of kt should then very well be just k over s plus a squared plus k squared? That's literally what I'm telling you. Literally what I'm telling you. Okay? So let's go have some fun. Now, the problem I started off with here a second ago was, where did it go? Come back here. So that guy right there. Okay, x squared plus 2x prime double prime plus 2x prime plus 10x. I could do equals 0, but that's too easy. I'm going to do e to the negative 3t just for fun. You with me? And then I'm going to do x of 0 is 4. X prime of 0 is 2. Okay. Now going into this, again, I always know on top of my head, I'm looking at this guy, I'm like, that sucker does not factor. R squared plus 2r plus 10, it doesn't factor. And in fact, in my mind, again, because I've been teaching this a while, I understand that that's probably going to give me a disgusting solutions, eigenvalues, if you will. But I'm going to roll with it anyways here. So let's have some fun. So it's going to be s squared x. And for now, I'm not going to put x of s. I'm just going to put x because it just saves some time here. Minus 4s minus 2 plus 2. And then it's going to be sx minus 4 plus 10x equals, and then that's going to be 1 over s plus 3. Now, all I'm doing, these are x of s's. It's too hard to keep track of them, so I just factor it out. I'm going to s squared plus 2s plus 10, and then equals 1 over s plus 3. Oh, shoot. Plus 4s, and that's going to be minus 8, and minus 2 is minus 10, so plus 10. Okay. And so what I'm going to do is simply go expand. Now, when I do this, you're going to think, Jay, this is a mess. And you're going to be right when you say that. So, parentheses 1 divided by z plus 3 plus 4z plus 10 What just happened? Escape. Escape! Oh, zeros. You idiot. It's supposed to be expand. Big dope. There we go. Beautiful. And you're like, oh, that's gross. Just hold the phone, friend. You haven't seen nothing yet. I'm going to write this down. 51z 13. And then it's going to be z squared plus 2z plus 10 minus, or plus rather, plus 131 over 13 and is there anything else it wants to tell us about? Yes, plus 1 over 13 z plus 1. By the way, am I shocked by that? Not at all. This is e to the minus t. These are going to be so cosines and sines. The thing that you're going to have to be a little careful of, and it takes a little bit of fancy manipulation here momentarily, is that to do this problem, we're going to have to crunch it down. We have to put these two guys together. Note that currently they have a common denominator. Frequently, though, this one might be over 26 or something, and you'd have to get a common denominator. Just be aware of it. It happens a lot. Now, we are going to have some fun. Okay? Now, what we need to do is we need to write this in a certain fashion. So what fashion, Jay? Glad you asked. So we need to complete the square on z squared plus 2z plus 10. It's been a while since you've completed the square. I just moved the 10 out of my way a little bit. So move it over here out of my way. So I'm going to look at this guy right here and I'm going to say, all right, how do I complete the square in this? I want to write this as z plus something squared plus something. Okay? So I do this. What's half of 2? It's 1 squared. So I added 1. I need to subtract 1. That gives me a 9 out here. You with me? And then this factor z plus 1 squared. And we're done. We're home free. So come back over here. I'm going to write this as 51z minus, well, we're not home free, but we're getting a lot closer to being home free. How about that? Does that make sense? So 13, and then this is going to be z plus 1 squared plus 9. Plus 9. Okay? And then, so when you do this, you know what we need to have. You know what we need to have. On top, we need to have this written as, this has to be written like the following. So it has to be able to be written as something. Well, okay, what we're going to need to do is we're going to break this into two pieces in a few minutes. But it's going to be, well, it's going to end up being 51 in this case. And then z plus 1 plus some more over, and then they're each going to have a piece of this. You with me? And so what's going to end up happening is part of it's going to be a sine function, duh, and part of it's going to be a cosine function, duh. Okay, and then we'll break it into two fractions momentarily. So to do this, what we're going to do is, and again, why z plus 1? Because z plus 1's on the bottom, that's what's got to be on top. So if you look at this, this is 51z plus 51. Well, I don't have plus 51 on top. Good Lord, I've got negative 131. That's right. So if you do this, you're going to like, well, what's the difference between 51 minus 131? Well, that's not right, Jay. Oops, I'm sorry. The difference between, so I got to go, it's 182 in other words, okay? So this needs to be negative 182 right here. So negative 182 plus 51 is negative 131. So what I have on top right now is the same as this, but now it's in the proper format. So now I can do this, finally. Minus this. And then I'm almost done, but not quite. Okay, now you got to be careful. Well, this is quite clearly 51/13 e to the minus t cosine of 3t, clearly. This is very similar because now I need a k on top. You with me? So I need a 3 up there. Now I can do this a couple of different ways. Does 3 go into 182? 9, 12? No, it does not. If it did, I could just divide that by that and I could pull it off. So what I do is put a 3 here and a 3 here. Okay? So it's going to be 182 over 39. And now this is, by definition, e to the negative t sine 3t plus 1/13 e to the negative t. What do you think? Let's check it out, dog. What do you think? So let's go to Desmos, desmos.com. 51/13 e to the negative x. What are you doing, stupid? Cosine of 3x. I forgot, is it minus or plus? Minus 182 over 39. What are you doing? Minus 182 divided by 39 e to the negative x sine See, this looks right. How would I know? What does it go through? 0, 4? Okay, so I made a boober somewhere. Oh, is it plus 1/13 or minus 1/13? Plus 1/13. Yes. Oh. There's your problem, stupid. Oh, no! No, 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 no! You idiot! Oh, you're a moron, Jay. You are a straight-up moron. Good Lord almighty. What is going on with you? You idiot. Oh, here's the problem. You see that right there? What a moron. E to the... There you go, stupid. Negative x. Hey, I bet it works now. What do you know? Negative 4 is my slope, is my initial condition, and what was my initial slope? It was 2. It was 2. Does that look like it has a slope of 2? It does not look like it has a slope of 2. Interesting. 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 So we're going to have to pause and figure out why that is. All right, in the original problem, it was 1 over s plus 3. Which means that our final equation over here, when you get over to it, you can get over to it, should be e to the negative 3x. Okay, so that's part of our issue. That's not all of our issue, though. Okay, that was part of it. Let's see if I can find the rest now. Well, good news, bad news. It's just I'm an idiot. I had this as a negative. The calculator had it a positive all along. So this is plus. So this is 51z plus 51. I need to get to 131, so I need another 80. Good night, nurse. That's embarrassing. Oh, shit. What? Oh, no. Oh, no. Goodness sakes. There it works, friends. God, I'm an idiot. There it is. There it is. There it is. Yeah. Apparently I can do math after I dink around with it for an hour. It's a little embarrassing. Let's try another one, shall we? What do you say? Okay, gonna do another one that's very similar to that. X double prime plus, let's do, I'll do an ugly one just to show you that the world is not perfect, friends. Although I would like it to come out decent. 9 minus 1 times 15. Well, I don't know. I don't really care. I guess it doesn't matter a whole whale of a lot. Yeah, let's do 10, I guess, again. Equals sine of 2t, sure. And x of 0 is 0, x prime of 0 is 1. Let's go have some fun. Before we get carried away, let's note, we know we're going to end up with something a sine k 2t and b cosine of 2t. We know that going into this thing. Duh. We also know that we're going to get r squared plus 3r plus 10 equals 0. We know it's going to be negative 3 plus or minus the square root of 9 minus 40. That's disgusting. I don't really care. Over 2. And that make it better or worse? No, it's just going to be gross no matter how you slice it. Ugh. So I know I'm going to end up with e to the negative 3 halves. And then some constant here, cosine of square root of 31 over 2, square root of 31 over 2 t, and then plus a c2 sine square root of 31 over 2 t. And I know that this piece here is going to tend to 0. So that means this whole piece here is going to be what we call a transient solution. This piece here is going to be our steady state solution. Okay? We know all those things going in. That's a fact. So we know that before we even start on this process, which makes our lives easier in a lot of ways. Okay, now again, I don't always do that, but when I see one of these guys that I know is not going to factor, so that means it's not going to be pretty, I usually go ahead and solve the complementary solution off to the side to at least know what I'm shooting for when I do my Laplace. I just think that makes my life easier. Minus 0s minus 1, right? And then I'm going to have plus 3, it's sx minus 0 plus 10x equals, this is going to be 2 over s squared plus 4. So that's going to be, when you factor the x's out, you're going to be s squared plus 3s plus 10. Okay, now this is just going to be 3 times 0 is 0, so you have a minus 1 here, so add 1 to the other side. Divide by this guy. Okay, so let's go ahead and hit expand on this guy first. Again, you could do partial fractions. I would never ask that you do partial fractions on that guy. It's just too much. Okay, you can see how, look, I'm pretty good, and I'm pretty good when it comes to algebra, and I mess stuff up all the time, and it's part of my job, and I still can't do it right all the time, and it's a little sad, but let's be honest, you could spend all day doing some of these problems and make a mistake somewhere, and then the whole thing goes to heck on you, and then you're very disgusted with yourself. So notice I've got z over 12, and the denominator is exactly what you think it would be, with the exception of the 12, of course. That part's a skosh different. And then plus, make sure I don't screw that up this time, 13 over 12 z squared plus 3z plus 10. And then, that again, those two pieces there I'm going to have to do some work on. And then the rest is going to be my steady state solution, minus z over 12, s is z squared plus 4, and then plus 1 over 6, be careful, z squared plus 4. Now that is not going to hurt me at all, okay? But if that 6 was here and this was a 12 here, I'd have to be careful of that. Okay, so let's do the easy ones first. This is 1/6. Oh, I'm sorry, that's a z on top, sorry. So it's 1/12 cosine of 2t. And this is going to be, well, I need a 2 on top. So if I put a 2 on the top, put a 2 on the bottom. So I'm going to have 1/12. That's plus now. Sine of 2t. Okay. Now these guys, I need to put them back together. So z plus 13 over 12. And z squared plus 3z plus 10. Okay. Now, I'm going to complete the square on that guy on a different page, I think. So z squared plus 3z plus 10. So z squared plus 3z plus 10. What's half of 3? It's 1.5 squared. 1.5 squared. Oh, shoot. 1.5 squared is 2 1/4. Oh, fart. So what I've really done is I've added 2 1/4. Therefore, I better subtract 2 1/4 over here. So this is going to be z plus 1.5 squared plus 7 3/4. Okay. Now, 7 3/4. So you're like, well, what is that? What is that going to be? Well, remember, this needs to be written as z plus 1.5 squared plus the square root of 7.75, if you will, squared. Does that make sense? Because that is going to be this is going to be my k right here, right? Okay. So let's come back in here. Now this is where this one's going to get ugly no matter how you slice it. That's part of the game of life, I guess, right? So down here I'm going to write this as 12 z plus 1.5 squared plus 7.75, right? Then on the top I'm going to have z plus 1.5. Now this isn't as bad as it looks, actually, and the reason it's not as bad as it looks is because there's nothing in front of the z here. You with me? So what I'm doing is that plus this 1.5 plus 11.5 is 13. Cool. Let's keep going. So now let's break it into two pieces. Z plus 1.5 over 12. Z plus 1.5 squared plus 7.75 plus 11.5 over 12. Yuck. Z plus 1.5 squared plus 7.75. Okay. This, by definition, is going to be 1/12 then e to the minus 1.5 t cosine of square root of 7.75 t plus, now look, I need to have the square root of 7.75 on top and on the bottom. That's disgusting. It is. So 11.5 over 12 square root of 7.75 sine square root of e to the negative 1.5 t square root of 7.75 t, there you go, minus this. We're home free, baby. Transient, steady state. I'm going to try to do this on Desmos here, I think, maybe. By maybe making this. Okay, I need my keyboard. One moment, please. This little tablet's good for some things, but other things it's worthless for. All right, here we go. So one. Now what I'm going to do is I'm going to actually pull the e out front, if that's okay with you. I'm doing it anyways. I don't really care. 1.5 t, or not t, stupid, x. There you go, babe. And then I'm going to go parentheses, and then I'm going to put in the 1/12. Okay, actually, do they both have a 12? They both have a 1/12, don't they? Well, I'm going to go with that then. So I'm going to stick to 1/12. I'm going to stick to 1 right here. I'm going to go divide by 12. There, babe. And so that's going to leave me with what here? It's going to leave me with 1 cosine of square root of 7.75. Don't forget to arrow over to get out from underneath of that guy. And then, what is it, plus or minus? Plus 11.5. Plus 11.5. Sine of the square root of 7.75x. Okay, now we're out of that. You with me? We're out of that. So we need to get out of that whole parenthesis. And then we need to go minus 1/12. Now they both have a 12th in common. So if you want to pull out the negative 1/12, I can. I'm actually going to go ahead and do that. I'm going to pull the minus 1/12 out. So minus 1 divided by 12. And then, of course, that changes the sign. So cosine of 2t minus sine of 2t. I think that's right. I think so. Now, how do I know if I'm right? Look at the graph, man. The graph should go through 0. Oh, it does. It should have a positive slope. does it. I think I should have a positive slope. I forgot what the slope's supposed to be. The slope's supposed to be 1. So if you were to graph y equal x, y equals x, that should be tangent. It's not, which means that somewhere along the line I went a little haywire here. So bear with me while I figure that out. Always something. Minus signs, 11.5. Oh, you see right there? It's right there, you moron. I forgot to divide by the square root of 7.75. Rats. Rats. Oh, it's like I know what I'm talking about or something. So here's what happened, you see. Initially, we had something going on. You can see there's a little wonky there. Look what happens over time, though, baby. Look what happens. We are approaching our steady state solution. In fact, what one could do is one could copy. No! Let's try it again without screwing it up this time. What do you think? Without screwing it up, Jay, can you do it? Probably not. Control C. Control V. Control V. Dude, look at that. See, initially you get some waves. Why do you get some waves? Because of the transient solution. As it goes away, and look at by 3 or by 2, basically, it's gone. The transient response is gone. All you have left is the steady state solution. Okay? Well, there's not a whole lot more to say about this chapter than that. It's really a matter of just crunching through them and doing them and getting comfortable with them. You will run into some that'll make you kind of scratch your head a little bit. But I think I think the easiest way of doing them is to just remember, always remember that as you're doing them, you know where you're going. You have a thought in mind. And again, as soon as I see one like, I don't know, x squared plus, if you saw this guy in a dark alley, it's this one's going to get ugly. 6x prime plus 25. I'm not going to do it, but that doesn't factor. It doesn't factor, which means it's going to get gross. And then I look at this, and in my mind, I'm going, geez, it's going to be 36 minus, yuck. Ugh. So I already know that it's not going to factor, and it's going to be complex, which means I'm going to have to complete the square. And I just know that going in. It makes my life a little easier. Now, there's one more thing I wanted to mention, and that is this guy. So e to the at times t to the n. What if you ran into this beast? What was the Laplace transform of this guy? Turns out it's n factorial over s minus a to the n plus 1. Where n is bigger than, where s is bigger than a, I'm sorry. S is bigger than a. There you go. Cool. And that's all there is to it. Okay? So if you look, here's an example of one of those guys. Yeah. Sure, I guess. So let me find one that's nice and sort of purty. I'm trying to find one of those guys that's going to make my life. Here, I'll just pause and I'll find them for us. So, for instance, here's an example of one. It's right here. It's not very hard. T to the 3 halves. E to the negative 4t. Okay. If you look at it here, our n is 3 halves. So that presents a little bit of a problem if you know how to do these at all. So we're going to talk about the top in a second, what n factorial is, what is 3 halves factorial. We'll talk about that momentarily. But on the bottom, you're going to have s plus 4 to the 3 halves plus 1 is the 5 halves power, I guess. Right? Now, to do to do the all right, so for reasons that are not abundantly clear at this point in your lives, you've probably not seen the gamma function. If you take, it comes up in statistics a lot. That's where I use it. The idea is gamma of n is equal to n minus 1 factorial. So for instance, if you did gamma of 7, you would get 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. Technically, it'd be gamma of 1, but gamma of 1 is 1, okay? And so what you end up doing here on this, guys, you end up with 3 halves. So if I want 3 halves factorial, that's gamma of 5 halves in essence. It'd be 3 halves times gamma of a half. Now, we know what gamma of 1 is. Gamma of 1 is 1. But gamma of a half, what is gamma of a half? Well, it turns out by definition that's true. You can also show it using the gamma function. It's an integral, and then evaluate it, and it comes out to pi, square root of pi over 2. So this guy comes out to be that right there. Now, what you can literally do if you run into one of these guys, you're like, I need 3 halves factorial. Literally type that into your search engine and go 3 halves factorial, right? And it will spit it out to you. It'll be 1.32, I think is the number it comes out to be in this case. And I'm okay with that. You can also on your calculator do it. And so you simply just go 1.5. Oops, try again, stupid. There you go. And apparently Betsy won't give us to us. Oh, you hate me. Oh, okay, Betsy's not going to do it. I must not have it in the right function. She should do it, but she's not going to. Excellent. So 0.5 factorial. It should give me that. So I'm in the wrong frame of mind. Well, I'm in the right frame of mind. I'm not in the mood to do it right now, to be honest with you. If you type it into your search bar, it'll actually spit that out for you as the proper value. Okay? If you Google will know how to get you there, and it's kind of a neat deal when it does, I think. Okay? Now, what would happen, say, if you wanted something to occur at a different value? So, for instance, let's say you had this function here. Let's say you had a function that was... you wanted x squared plus 2. You like x squared plus 2. Here it is. But darn it, you'd like to scooch it over 3 spots, right? How would you do that? Well, you would do f of x minus 3, obviously, and then there would be x minus 3 squared plus 2. We call that a translation, right, in the x-axis. Okay. Ooh, darn. So just be aware of that. So when that happens, what you're going to end up doing is the following, okay? You will do the following. You will see that it becomes this, the Laplace transform of e to the at f of t, okay, in reality it just becomes f of s minus a, like so. Now, give an example of that. Sure, love to. So, and again, that is, again, where we came up with those guys, if you will, the cosines and the sines ones. We translated them. Now, next section, okay, we're going to get into some more of that sort of thing, but we're going to do it a little bit differently. We're going to talk about, well, what happens if I don't want this thing to turn on? Actually, not the next section. The next section after that, I believe. What if I want this thing to turn on at a certain time? No, I can totally do that. What if I want it to shut off at a certain time? I can do that as well. And so we're going to talk more about that. In other words, I want this guy to now look like this, right? And so it would be, well, how do I go about doing that? And so we're going to talk about that. So that will be coming up soon. Okay, we'll be doing things like where you'll be doing things where you talk about, this is what I want to happen, but I want it to happen when t equals 3. For instance, I want to flip the switch on my RLC circuit. That's when I want to give an impulse, some force, oomph to the system. So we're going to get to that as well. So just be aware of this. This one here has to do with the translation that we talked about today, which we didn't really talk about in terms of a translation. But where these guys here, where we ended up with, well, those two. But these guys here, where we ended up with having this e to the negative, in this case, it was e to the negative 1.5 t times our function. Okay? And so that was a translation in the s-axis, but we're going to be doing translations in the t-axis next time. Okay? and talking about how is that going to affect ourselves. Okay, so a little bit different in terms of that, and you'll see what I mean when we get there. So that's what we're doing a lot this week. Is pretty much the ones that I picked out for you in section 3 have to do with basically if you can play this game, you're good to go. Remember, always check your graph on Desmos. It's almost impossible to screw it up. Like Desmos, I mean, you type it in, right? Jay has a hard time typing it in, but it's easy to see if you're right or not because does it match the initial conditions? And the chances that you got the function wrong, but they match up with you found a different, randomly you found a different function that matches those two initial conditions, the chance of that happening is nil. Okay, so if it graphs right, hey buddy, you're right.